So I had another slide in here, but it's gone. I'll put it back in when I send the slides out. If you have a very, if the actual chance of being positive is quite low and you have a high proportion of people who's unaffected, it's going to end up that your positive, even though you have pretty good sensitivity and specificity, your predictive values are not going to be great. So, find this here. I can't find the actual data, but it's generally the, for example, the skin tests are pretty good at predicting people who won't get TB, right? If you're negative on the skin test, you're not going to get, the predictive value is pretty good that you're not going to get TB. But it doesn't have a great positive predictive value because most people who are positive don't get TB, okay? And if you're in a situation like South Africa where 80% of people are positive on a skin test, it's not a very good predictor because basically you're saying that almost everybody could get TB just based on that skin test. So you don't want to, you can't really treat 80% of your population for TB. So what you want to do is try to figure out who you should treat. In the paper, here's a depiction of how well the current methods work. So here, all these squares are 1,000 people, and the black are this 80% positive PPD or cytokine assay in South Africa, okay, and 20% negative. And then the TB cases are these in yellow. So most of the TB cases are coming from the cytokine positive people, and presumably these 3 are people who just got the infection, or maybe they had some reason they didn't react in that cytokine test. So in order to avert these cases, I think there's like 7 cases here, they have to treat 135 people to catch all of these, just based on only the cytokine assay. So, you know, they're probably not going to do that because it would be too burdensome for everybody, and nobody wants to take that many drugs. Okay? So what they did was they took blood samples and did transcriptomics on the cells in the blood sample, looking for a signature that disease was going to happen. Okay? And they don't have any idea what that was going to be. It's a whole genome-wide, let's see what we can find, and let's use machine learning to try to find things that correlate with later progression to disease. So they had these people, and they had a set where they knew these people went on to get disease and these people didn't. So then they could compare these blood signatures of the people who went on to get disease and the people who didn't. So here's an example of taking a look at the transcript levels of a non-progressor and a progressor for a particular gene, SERPING1. And then they plot the signal on the y-axis. And then they do the same thing from the transcriptomics for APOL1. And then what they did was they looked for the relationship of these genes, how well the two together could predict progressors versus non-progressors. So you can't really see the green on here, but there's a lot of green things in here. But we could see that we're enriched for progressors having that relationship of the signal. So they did this for all the genes pairwise. And then they start connecting the pairs and trying to see which ones give them a better way to discriminate progressors from non-progressors. So these guys are actually computational biologists. They do a lot of programming. You know, they know how to code. They do that. They know some biology. Dan Zach knows a lot of biology. He's at my the people in the lab are coding stuff, and they're like doing things I don't really fully comprehend, but they build on the work of the lab people collaborating with the computational biologists. So they ended up with something they called the core classifiers, and they take the data for each. So here's all these different relationships of their, I think they had certain number of primers, and they're looking at the signal they get from all these different relationships of gene expression. Then they made primers to them so they could do the task just with PCR instead of doing RNA sequencing of the whole transcriptome. And so they're looking at the relationships of these, and by the relationship they're scoring them. If the relationship between this one and this one fits a certain value, they call it, it's like a progressor and it got a red line. And if the relationship between this and this was like a non-progressor, they scored it as non-progressor green line. So these images look the same, but what they're showing you is the scoring. Okay, so this one, everything voted as progressor. This one, relationships voted as non-progressor, but a few voted as progressor. That was still called non-progressor by the computational algorithm. Okay, does that make sense to you, more or less? So basically what they found, using these 16 genes, that they had 60% sensitivity and 80% specificity to be able to predict progression to to active TB. Then they went, that was in their training set. Okay, so they had the set where they know the answer, they did the computation, they said, okay, we've done it as best we can and it can predict this sensitivity and specificity. Then they have other sets of data that they haven't used to develop their algorithm that they've been tested on. Okay, so it's not, they haven't biased their algorithm to make it detect those specific samples. So they got the same result when they retested their algorithm on different sets of samples from different places and so on. And it also seemed to work on HIV positive people. So the sensitivity and specificity doesn't sound great from this, but let's look at it from this point of view. Okay, this was before they had to treat 135 to avert one case. Now, basically, they have to, so they treated 800, had to treat 135 to avert one case. Here they're only treating 243 people, and they averted one case per 43 people. So they've basically gotten it about 3 or 4-fold better reduction in who they think they should treat. So this is just a first step of trying to figure out who should we treat in order to prevent progression to TB. So basically they've got a signature that allows you to more efficiently predict who should be treated, down from 800 to 300. They're working now to improve the algorithm, and they've also tried to reduce the number of genes that have to be tested. So now instead of 16 genes, it's down to 6 with no loss of sensitivity or specificity. All right, I want to move on to just mention a few other things before we get into drug treatment. It's really critical that we can identify and treat HIV positive TB patients because they have a disproportionate impact on transmission. Latent HIV positive people infected with TB in particular, if they become active, they are 12 to 20 times more likely to convert from quiescent to active TB, and then that increases the number of people infected people that spread the disease. Okay. Also, TB disease progresses more rapidly in these patients. They have both extrapulmonary and pulmonary TB. We've already talked about the diagnostic challenges. If you don't know that they're HIV positive, we can miss that they're infected. We may not be able to know that unless we may not be able to assess that unless we know the HIV status. And areas with high HIV-TB co-infection coincidentally also have a higher proportion of drug-resistant strains. So that adds to the complication of treating those people. TB mortality in HIV-positive people is double that of HIV-negative people. So basically, what we have is the reason that TB and HIV interact so strongly is that people who have HIV, who are co-infected with HIV and are not treated, which is a lot of people, and they get TB infected, they're more likely to get active TB, okay? And then they're going to spread it. It's not just them that's getting sick, they're going to spread it to other people. So that's the main problem, the big problem, and they're more likely to die themselves. So basically, we want to find those people, and as soon as they start to have any issues, we want to treat them for TB. Also, we want to treat them for HIV. And if we can control their HIV levels, they're not going to have, they're going to be more like an HIV negative person as far as latency goes. So moving to drugs, until antibiotics, treatment was, fresh air, rest, and surgery. So sometimes they would just go in and cut out part of your lung or cut out your whole lung if you had a problem with a bunch of TB in your lung, just doing surgery and cut out a lobe or your lung. And then here's pictures of people, they had to be, I think, they felt that cold air and rest was the best treatment. So they would be in these cold places, wrapped up in bundles, breathing cold air. And there were a lot of kind of TB refugees that moved out to different climates in order to try to help their TB. Some of these cities you probably aren't familiar with, but they're out in the west where the air is dry and clear. So for normal TB, we use a combination therapy, usually 6 months, 4 drugs. And those drugs are not new drugs, those are old drugs. I think the latest was in 1966. So they aren't, we need a long course of treatment. So every person who's got active TB has both active TB in their body and some TB that is still not as active. Some clones or clusters of TB that are quiescent in their body, and then some that are actively growing in their body. So the drugs seem to work really well with the ones that are actively growing, but the quiescent TB is slowly becoming active, increasing, then you treat that. And also they have a large burden because they've had enough TB replication to have many bacteria in their bodies that you have to kill. So there's a long treatment, 6 months, and resistance is rising. So we use combination therapy. Again, we've gone over why you have to use multiple drugs so that you don't get mutations. And also, one of the strategies for treatment, because compliance is difficult for this disease, is they use directly observed therapy. So a nurse or a healthcare worker will come to your house and watch you take the pill to make sure that you take the pills. Because otherwise, people will start to feel better and they don't want to take the pills anymore because the pill is a bother and some of them might not agree with you. make you feel a bit ill, but you aren't cured yet, so a nurse will come and watch you take your pill. So the targets of the first line drugs all attack critical molecules for the proliferation of the bug. So we have isoniazid, inhibits cell wall synthesis of the bacteria. Rifampin targets the bacterial RNA polymerase, which is completely different from our RNA polymerase. We have ethambutol, cell wall biosynthesis. Pyrazinamide, at the time that I made this slide a couple years ago, the exact target was not clear, but it does disrupt energy metabolism. So these are mainstay drugs along with streptomycin, which is antibiotic. So all the drug resistance arises from mutation in TB. There's not reassortments or anything like that, and I don't believe there's any sign of plasmids or that type of DNA uptake. For isoniazid, resistance arises by mutation in the target enzyme or mutation in an enzyme that activates the drug. So the isoniazid has to be activated by an enzyme in TB, and then it can kill TB. So you can mutate either one of those. In rifampin, mutations in the target in RNA polymerase. There's a lot of derivatives of rifampin-like molecules in some of these. You get cross-resistance, and sometimes you don't. So it's very specific for the mutations in the drug. For MDR-TB, that's defined as being resistant to rifampin and isoniazid. So you could have drug-resistant TB, just resistant to one compound, but MDR resistant to those two specifically. And for treatment of them, they take twice as long to become sputum smear negative. So if you are sputum smear positive, you can transmit. Once you're sputum smear negative, you aren't transmitting anymore. You still have TB in your body, you're not cured, but you aren't transmitting. So it takes twice as long with MDR-TB. And they have a cocktail of at least 4 drugs. They can't use those two, isoniazid and rifampin, for 18 to 24 months. And that costs up to 100 times more than the normal course of therapy. So bad news for that. Okay, so then it gets worse. We have XDR-TB and TDR-TB. So XDR, extremely drug resistant, are resistant to rifampin, isoniazid, fluoroquinolone, and an injectable drug. And then there's TDR-TB, which is also called XXDR-TB, is resistant to all first and second line drugs. That emerged in India. I mean, it's emerged more than one place, but in India it emerged in 2011 in Mumbai. And WHO has come up with a new 9-month protocol for XDR-TB, which normally would be 18 to 24 months. But the form that is in the TDR form in Mumbai can't use the short protocol. So I have this quote from Drs. Udwadia, who identified these TDR patients. He said, "This has as much chance of working successfully in India as the proverbial snowflake in hell." So, because those patients are already resistant to 3 of the 4 drugs used in the short protocol. So here's a picture of the global distribution of TB, MDR-TB, and XDR-TB. So TB incidence, MDR-TB, XDR-TB, this is just whether there's been a case or not reported, not any quantitation beyond that. So I think in India there's been over 25 or so XDR-TB cases. XXTBR cases. Okay. Question for you. So the R naught for TB is about 10. What is the relationship of the R naught for TB and MDR TB? I think you're going to get this pretty quickly. Has everybody got the answer? Anybody want to volunteer what they think? What your neighbor thought? You can blame it on your neighbor. Yeah?
I think it's C.
C, yes. Yeah, we just mentioned that it takes a longer time to clear your sputum if you have drug-resistant TB because you're using drugs that are not as effective. The first-line drugs are more effective at eliminating TB, reducing the burden in your body. So, yeah, that's exactly correct. All right, now I want to show you a video, and I'm hoping it's going to work. Let's see. XDR-TB in Tajikistan. It said she likes to draw. So basically, we need new drugs. We do have a couple new drugs that did come out, bedequalin and one other, which name I can't remember, that are being used. We need simpler, shorter approaches, but still affordable for drug-sensitive TB, so that we can just ensure that people take their full course and we don't get them relapsing and get drug resistance. And we need better courses of treatment for drug resistant. We need short, simple courses for latent TB. So, you know, even if we can predict if you're going to get TB or not, having somebody take 6 months or something of drug is, you know, it's going to be very hard to convince people to do that when they don't feel bad at all, for example. And we want to have drugs that don't have drug-drug interactions, so that they, you know, taking them for 6 months or a year isn't going to interfere with other medications that you might have to take. Particularly people with HIV who are also on their own cocktail of medications. Okay. So that's it for TB. Any questions people have about TB at this point? Is anybody here working on TB? Okay. Okay, so our next session is going to be on malnutrition, and I think at this point we are going to have a brief group meeting about your debate topic for like 15 minutes. So, but just, this is on your handout. Just be aware that you're going to be preparing for that on Monday. But I think you should talk with each other a little bit about your debate topic. I know some people aren't here. And I want to remind you that on your handout that you got by email, that you have the format of the debate topic. So we're going to stick with that format. And it's sort of, you know, the pro statement, the con statement, the rebuttals, and the summation. And so you're going to have to figure out, everybody should do part of the presentation. But you can decide between you who's going to do how much. So if you've only got 2 people in your group, you've just got 1 pro and 1 con. Sorry. Hopefully you'll get one of your members back. And start thinking about ideas of what you want to cover on both sides, so you can get started on doing a little bit of reading, you know, so you aren't doing it all like the night before, because that will make for a difficult situation. Okay? So why don't you guys chat for a few minutes before we close for the day? I don't know. I'm not going to tell you right now. You have to be ready for the first day. Be ready for the first day. We'll decide when we get a little closer. Some people might, if you want to present on the first day, let me know. Because otherwise,